Hello, I'm Michael O'Connell, and in today's video, I would like to start examining some substitution and elimination reactions. So let's take a look at our starting material here. And the first thing I want to emphasize whenever you're doing substitution or elimination reactions, the first thing you need to do is figure out if your alpha carbon, that is the carbon bearing your leaving group, is primary, secondary, or tertiary. Because if it's primary or tertiary, there are some possibilities that we can eliminate. So let's take a look at our starting material here before we even look at what we're reacting it with. And we obviously see that we have our leaving group, and bromine is a good leaving group. It's a halogen. It's down the group, the column there, and it is quite big, so it's able to delocalize negative charge quite well. So we know that this obviously is going to be our leaving group. The carbon bearing that leaving group is right here, right? And it has two hydrogen atoms that aren't shown, and then it's bonded to one carbon atom, making it primary. So I'll put that down there. Okay. That's good for us. Now, what is going to happen next? Now we have to look at our reagent. What are we reacting it with? And then we have to ask ourselves the question, is it a strong nucleophile, or is it a strong base, or is it some sort of combination? So obviously we have NaOH, sodium hydroxide, and it's going to be broken up into its ions. So the one that we're concerned with is the one with the negative charge, which is hydroxide. Hydroxide has 3 lone pairs of electrons on that oxygen atom, so it can readily use one of those lone pairs to form a bond in which it can function as a great nucleophile. And obviously, we know that it's a strong base perfectly capable of pulling off hydrogen atoms. But in this case, we do have a primary substrate or alpha carbon, and that's very important for us. So we know that an SN1 or an E1 reaction is not going to occur. And the reason that's not going to occur is because in an SN1 reaction or an E1 reaction, a carbocation intermediate is formed. And that carbocation intermediate needs to be stable enough to actually be formed. And primary carbocations are not stable at all, and they're not formed. So that's 2 of the 4 possibilities that have been eliminated. So that's great. And that just further emphasizes the importance of figuring out what your substrate is, if it's primary, secondary, or tertiary. Okay, so OH minus, it's a strong nucleophile, it's a strong base. So we could have E2 or SN2. What I want to emphasize here is that the SN2 is going to be your major product. You should not worry about E2 here. Now, why do I say that? Well, OH minus is very small. It's not going to be sterically hindered at all. So there's nothing stopping it from being such a good nucleophile. And because of that, coupled with the fact that it is a primary substrate that we're dealing with, the SN2 reaction is going to happen so quickly that you're not going to get much product from any E2 reaction. So in this case, we are only going to get one product, right? So realistically, this is going to react with the OH minus, and it's just going to be literally one step. This bromine is going to leave, and at the same time, this OH is going to add with its lone pair of electrons and form a bond to our carbon all at once, okay? Now, you might be worried about inversion, and that's a good thing to consider, obviously, because we know that when we have an SN2 reaction like this, so this is SN2, that inversion does occur. And all that really means is that we're saying that although this process happens simultaneously, this OH is going to add opposite to the leaving group. Okay, so your nucleophilic attack is going to come from the opposite side of the leaving group. But in this case, do we really have to worry about that? Well, not really, because we know that there's 2 hydrogen atoms here, right, that aren't shown. And obviously, this is sp3 hybridized, and this is a single bond here, so we have free rotation. So there's no reason to be concerned. So you're literally just going to replace the bromine atom with your OH group. So this would be your final product. You would have your cyclohexane ring and then your OH. And that's going to be your major organic product. Okay, now there is something else that we could do that relates to what I talked about, specifically how I explained that any reaction for the E2 in this case would not lead to a major organic product. However, the only exception to that is when we do have a very sterically hindered molecule that is a strong base but a weak nucleophile. And the most common ones that you'll see are tert butoxide or LDA. So LDA, I believe, is lithium diisopropylamide, and it looks something like this. So I said diisopropyl, right? Okay, so we have 2 bonds to the nitrogen, but that means it has 2 lone pairs, right? So it's going to have a negative charge, and then we have our lithium. So as you can see, this is quite big, and these isopropyl groups, these are going to cause a lot of steric hindrance, okay? Meaning that the lone pairs are going to have a very hard time attacking and forming a bond and acting like nucleophiles. However, we still have a negative charge, and because of that, those are going to be able to pull off protons and be very strong bases. So that's what's going to happen here, right? So let me just erase that so we can kind of draw what happens here with this mechanism. So we're going to get only the E2 reaction. And what would happen here, so instead of this lone pair attacking our alpha carbon specifically all at the same time with the bromine leaving, we are going to have this act as the base, as I said, and it's going to pull off a proton. Now, as you can see, we only have one branch coming off of our cyclohexane ring, okay? And what that means is that these carbons, and actually because I didn't indicate stereochemistry with this group off of my cyclohexane ring, these carbons are basically equivalent, so you can attack either one, it really doesn't matter. But it's going to pull off this proton, and then the pair of electrons here from that bond are going to go right into here, okay? And once again, another thing to emphasize with the proton that is being pulled off in any E2 mechanism, you can only pull off a proton from a carbon that is adjacent. And what I am now realizing is that I have made a terrible mistake, haven't I? Because these hydrogens, although, like I said, they are equivalent, they are certainly not from carbons that are adjacent to our alpha carbon, which we will commonly call beta carbon. So hopefully you see that mistake I've made, right? Because there's a carbon right here. This is a carbon. That's the only place that we can really pull off a proton because we don't have a carbon over here or here or here. So that is very much something to look out for. You do not want to make that mistake on the exam. So we have this hydrogen here. And for all intents and purposes, we can assume that this can rotate in some way, this hydrogen atom, to be anti-periplanar to our leaving group. And I'll talk about that a little bit more later, possibly. But we're going to pull that proton off, and then these electrons are going to form the double bond. And again, this carbon is adjacent to our alpha carbon, but all at the same time, our leaving group goes away. Okay, so then our major product here is going to be an alkene, and it is going to look like that. So that is another good example here, and that one is obviously for elimination, E2 specifically. But the reason I did that example is because that's the one time with a primary substrate that you could have an E2. So really the only time you're going to have an E2 reaction with a primary substrate is when you have some very large, very strong base that's not a nucleophile, like LDA or tert butoxide, which is why primary substrates, when I'm taking exams, are my favorite, because they are usually SN2. Okay, but what if we had something like water, right? Well, obviously this oxygen now has 2 protons, and it doesn't have any negative charge, so it's probably not a strong nucleophile, and it certainly isn't a strong base because it's water. And what this means is that an SN1 or an E1 reaction could occur, right? But once again, we have to start with what our alpha carbon is. Is it tertiary? Is it secondary? Is it primary? And it's primary. So no reaction is going to occur here. No reaction. Okay? Because it's primary. Nothing is going to happen. This is just not a strong enough nucleophile that it's immediately going to attack simultaneously as the bromine leaves. It's just not going to happen. And if I didn't say it before, the E2, similar to the SN2 reaction, is one step. So there's no intermediates that occur. Okay. So let's change things up a little bit and try some other reactions. Now let's take a look at this reaction. So what's the first thing we need to do? Once again, we need to figure out where our carbon is that has our leaving group. And our leaving group is going to be iodine there. And then that makes this our alpha carbon, okay? And as we can see, our carbon bearing our leaving group is bonded to this carbon and this carbon. So it's secondary. And yep, I'm going to be honest, these are my least favorite because there's a lot of possibilities. Because when it's secondary, it really doesn't eliminate any of the 4 possibilities necessarily. You have to look at your reagent. So that's what we're going to do here. And our reagent, fortunately, doesn't have a charge, and it has the proton attached to the oxygen, which the oxygen has a couple lone pairs. But we know that methanol, water, things like that, they're weak bases and weak nucleophiles, which is very, very fortunate for us, right? Because this way, we can at least eliminate the SN2 reaction. Now, what about the E2? Well, the reality is it's not a strong enough base to do an E2. However, there is one comment I would like to make about E2 reactions that I vaguely mentioned before, which is that the proton that is removed in an E2 reaction mechanism must be anti-periplanar to the leaving group. Now, what the heck does that mean, right? So if you did Newman projections where you look down a carbon-carbon bond and you have something like this, right? At least this is the way it was shown to me, right? So like you're looking through the board here down a carbon-carbon bond and you have the 3 groups on each carbon. It means that the dihedral angle, so between your main groups, so like we have X and Y here, would be 180, right? And that is what you want for, like, if X was your leaving group, and this is the proton that is removed. That's what they mean by anti-periplanar, okay? Because obviously they're in that same plane, but they're anti in the sense that they're 180 degrees apart based on the dihedral angle. So what does that look like for us? Well, when we're thinking about a chair conformation for this, let's draw that. This is a good review. I'm right-handed, so I'm going to draw it like this. It's not great. I'm not great at chair conformations, admittedly. Okay, so let's draw our wedge up, axial, right, for our leaving group I. So if it's anti-periplanar, it definitely needs to be trans. And again, anti, meaning the angle is 180, the dihedral angle, it certainly needs to be down, right? So what would be down here? Well, unfortunately, this is the adjacent carbon to our alpha carbon that would be here. And because this methyl group is trans to the iodine, it's going to be down. And then we would have some hydrogen that is up and equatorial. So that would not be able to be removed. And obviously, you would have a hydrogen over here that is down, which would be anti-periplanar. But what's the problem with that? Well, the problem with that is that suppose this was a strong base and it removed that proton and this formed a double bond in here. Well, your leaving group would have been gone. So your double bond is not very substituted. So would that product form? Yeah, possibly, but it's not going to be a major product. So we're not going to concern ourselves with it. But fortunately in this case, methanol is a weak base and a weak nucleophile. So we are going to get an SN1 product or products and obviously an E1 product or products. Let's just see what happens first, okay? So the main thing that we have to realize when we have a secondary substrate is that hydride shifts can happen, especially if we're concerning ourselves with the E1 or SN1 reaction mechanisms. And the reason for that is, again, a carbocation is formed. And we want that carbocation to be stable, and it's going to be most stable if it is tertiary. And it will try to make itself tertiary through hydride shifts, if at all possible. And what do we see in this case? So for our mechanism, if we were going to kind of draw this out, right? So what happens in the first step? Leaving group goes away, goes bye-bye. And then we have our cyclohexane ring, okay? And we have our positive charge here, and we have our methyl here. But what that means, obviously, we have a hydrogen wedge. Man, that's a bad wedge. But it is a wedge nonetheless. So what this would mean is, look, this carbon has 3 carbons bonded to it, so we could try to get the positive charge there since our positive charge is adjacent by moving this hydrogen over, okay? So then we get this, right? Now notice one thing that is super, super important, and hopefully you can see my methyl group. But as you can see, I drew this methyl group in the plane because remember that this carbon now is just bonded to 3 things and it's electron deficient. So it's going to have that trigonal planar configuration. What's very important for us to realize is that the nucleophilic attack in an SN1 reaction mechanism can occur from above or below since this methyl group is in the plane. So that's just something that we do need to consider. Okay, so what about our nucleophile, right? So it's going to be able to attack. So if we attack this positive charge with our methanol in SN1, and I'm just not going to do the extra step for right now of the proton loss. So we get a bond there. So this would be one of our products, right? Certainly. And obviously, yeah, I ignored the proton loss. So we have the OCH3. Now, we could also indicate these as wedges and dashes, but we really don't need to because they're bonded to the same carbon, and we know obviously they can't both be up or both be down. So I'm not going to worry about that too much. Okay? And then what else could happen here? Well, as I said before, now with looking specifically at our tertiary carbocation, the protons here and here, they're equivalent. So you could pull off either one, right? So if we have a hydrogen, pull that off, and then that bond forms in there, okay? So then we get a very, very substituted double bond there, which is awesome. Okay? So these two would certainly be major products. They would also want you to indicate the secondary carbocation and the products that would come from that. So what would come from that? Well, once again, your lone pair would just attack here, right? Okay, obviously it can attack either way, but these are somewhat important, right? So what would these be? These would be diastereomers. Ooh, big word there, right? If you remember the con angle prelog rules of labeling RNS and getting those assignments, that's extremely important, right? And the reason I say that that's important that they're diastereomers, right? So these two groups are cis, and then now these two groups are trans, is those are different molecules. So unlike enantiomers, which are obviously non-superimposable to each other, they are the same compound, right? So that is very much important for us to realize. Now, these, I guess I would say, are your four main products. Now, you might be asking, well, Michael, why didn't you do the E1 reaction mechanism for your secondary carbocation? And the reason I didn't do that, actually, is if you pull off this proton here, you would end up forming that double bond in there. Okay. And you wouldn't pull off this proton because then you get the double bond here, which is not going to have your methyl group as one of the substituents, which means it's just not going to be a major product. So it basically would form this again. So you don't need to really include that necessarily. But the key thing to understand with this type of reaction is you have 1, 2, 3, 4 products. So let's label R and S, since that's just good practice. So we have our oxygen as the first atom we get to here, right? So that's probably going to be our first priority. Then we go carbon and carbon, but then this has a methyl group, so this would be higher priority. And then the hydrogen that's not drawn there is a wedge, so it's in the back. So that's perfect for us. So then we can do the kind of clockwork. So we have 1, 2, right? And we're going like that around. So this is R, okay? Now, what about this, right? So we have a methyl group, and then we have the rest of the ring, and then we get to an oxygen. So obviously this is going to be a higher priority. We have a 1 and a 2, and then we have a hydrogen that would be coming out of the page at us here. Hopefully you can see it. So it'd be a wedge, and then you have your third group there. But what this means, so instead of going 1, 2, 3 like that, because the hydrogen is in the front, we are actually going to go in reverse order. So that means instead of going 1, 2, 3, we're going to go 1, 3, 2. So once again, we're going to be R. Now, this doesn't change, so this is going to be R, and then this is going to be S. So as you can see, those are going to be diastereomers. They are different molecules, and you do need to show them in your answers. So I know that was kind of long. It was honestly a little bit longer than I expected, and I tried to explain as much as I could as I was doing it, so feel free to watch this on a higher speed to get through it a little bit quicker. Once you're really, really good at all of this kind of stuff, probably a lot better than I am. But hopefully this video was still helpful for you, and I just thank you so much for watching.